Okay, I'm gonna have to get my headset here. Sorry, let's pause this. Okay. Okay, greetings. Hope this is coming through okay. I'll just check some things here. I need to close some programs that I'm running here so as to make sure that okay, make sure that everything's working fine here. Okay, good. So then, all right. So last time we were discussing logarithm functions, exponential functions, logarithm functions, and especially looking at graphs and shifting of logarithms, logarithm functions, and exponential functions. Okay, today I want to continue with section 6.5 of the textbook, Abrahamson, which deals with the properties of logarithms. Or logarithm properties. Okay. So these are properties. Some of them by now are pretty simple and obvious. So but they're illustrated by examples. So when in doubt, when the property looks a little bit tough to understand, it's always worthwhile to check a few examples, simple examples first, to convince yourself that these properties are true in general, and hopefully it doesn't take too long to realize that if it holds for a few simple properties, for a few simple examples, it might not be true in general, but it might need to be proven some other way. But hopefully the simple examples will give you the idea of proving it for the more general case. Okay, so one property, some of the properties, two of them are called the inverse properties. And these have to do with the fact that the logarithm function is the inverse of the exponential function. So what that means is if we take the exponential function of x to base b, and then you take the log base b of that, you get the original argument which was placed into the exponential function, namely x. Okay, so it's just a restatement of f inverse composed with f of x. Gives you, when you plug x in there, it gives you the original value. So, in other words, f inverse composed with f is just the identity. And how can we read this? Okay, well, log base b of a number is always the number to which you have to raise b to get this number originally. And what do we see right here? Well, we can already see that must be x, because this is, we're explicitly raising b to the power x inside this argument. So the answer to the question, what raised to the power b? What do you have to raise b to? What power do you have to raise b to get b to the x? The answer is just x. Okay, so that's pretty much more or less obvious. So Another way to see it is just rewrite it in the corresponding exponential form, and you get, right, replace this by b to the x is equal to e to the x. So it's just an identity. That's the exponential form of this logarithmic form. So that's one property. Another second property is you can compose in the other direction. Okay, so the identity, remember this composition holds for f must be 1 to 1, and this identity is true on the domain of f. And the result will be, yeah, the identity. Any element of the domain of f, when you plug it in here, will give you f of x. And that will be, like we tell, that's automatically in the range of f inverse. So already in the range of f is already in the domain of f inverse. The range of f is the domain of f inverse because the two inverses have the same. The domain of f is equal to the range of f inverse, and the likewise vice versa. Okay, just to say that this is well defined if you plug in x restricted to the domain of f. Okay, this means that once you do the first operation f of x and plug it into f inverse, then that will be well defined as well, and you'll get the original value of x. And this is also true on this is true on the domain of f, and this is true on the domain of f inverse. You just replace. Yeah, you'll see this property will work to show that this is all well defined. Okay, and so now applying this to the this other property here, we just get b to the raised to the power log base b of x must be x. Right? So again, this says this is the power to which I have to raise b to get x. Well, I'm doing that. I'm taking b, I'm raising it to this power, so I should get x. Okay, so again, rewriting it in exponential, or this is the exponential form, write it in the logarithm form, and this argument goes over here, and this x goes over here with b replaced by log base b. So again, the logarithm form expressing the exponential form in logarithm form does the trick of showing that they're the same. Both sides are the same. So this is an identity. Okay, now there's also an important property called the one-to-one property. And this is now, because we'll see a lot of in this section, a lot of exponential equations or logarithm equations. So the one-to-one property for logarithms, my pen is running, it's getting pretty dry here. Let's try this one. All right. The exponential property, the one-to-one property for logarithms, okay, says that if log base b, so if you have two logarithms with the same base, they're possibly different arguments m and n. But if you know that the logarithm base b of m is equal to logarithm base b of n, then, well, this is true if m equals n, because the logarithm base b is a function. So, yeah. So that's pretty much obvious. But it's also true that if the logarithm of m is equal to the logarithm of n, both base b, then m is equal to n. So the implication, the hard implication, easy one is going the other way, but the hard implication sign is that, does this prove this? And the answer is yes, because the logarithm function is 1 to 1. So that's why this is called, as long as m is greater than 0 and n is greater than 0, this is called the logarithm property, or the 1 to 1 property for logarithms. There's also a 1 to 1 property for the exponential function. Which I might have alluded to before, but that's also because, so the base b raised to the power x is equal to base b raised to the power y implies x equals y. That's the 1 to 1 property for exponentials. Okay, so it's maybe let's call it 3a. This is then should be 3b. Okay. So now this is the principle of this section. One of the principles is that because the exponential and the logarithms are inverses of each other, properties which hold for the exponential functions can be kind of translated into properties for the logarithm functions. So let's see how this works for products. So product rule. So you're familiar with the product rule for exponentials. Product rule for exponentials says that if you take the product of two numbers which are base b raised to some power and base b raised to another power, let's say b to the x times b to the y, you take the product of those, then the result can be obtained by simply taking the same common base and adding the two exponents and taking the base with respect to that sum. So b to the x plus y. So we have a product rule for exponentials. This is something that hopefully you're familiar with from Math 101 or Math 99, whatever you might have seen this. But we could now translate this, or see how this works for logarithms. So the corresponding rule for logarithms is called the product rule for logarithms. And the idea is when we look at x plus y, that will correspond to a logarithm. Okay, so it's a power to which we have to raise b to get another number. And essentially what it translates to, as we'll see, is this log base b of m times n. So that's a product, not a sum. That gets changed into a sum of the logarithms. So here the product is of the whole numbers and the bases. The base raised to the power is going to be one of our m or n here. And over here, that's what we get. Yeah. So over here, in the logarithm expression of this number, the logarithm will be the sum of the starting logarithms. Okay, so let me then write this out more fully. So let me call this x to correspond with the this factor here. So if I call that x, and this is called y, then if I write, okay, so what this is saying is that x is equal to log base b of m. And I'm assuming m is greater than 0, n is greater than 0. So that these expressions are all well defined. Because I need the arguments to be positive in order to take the logarithm. So this is the definition of x, and the definition of y is log base b of n. Okay, so these are intermediate definitions. Starting numbers m and n are given, b is also given, and in order to prove this identity, I'm going to introduce these intermediate variables defined as the separate logs. All right, and so if I define these, then equivalently I can write them as in their exponential form as b to the power x is equal to m, and then this one b to the power y is equal to n. All right. And now the expression x plus y, so I want to show that the log base b of m times n is simply equal to x plus y. But what's the equivalent expression to this? Well, if I raise b to the power x plus y, I should get mn. But this is true because if I take these expressions here, I get b times x times b times y. And we know that's true from the product rule. So that proves this property, which is the product rule for logarithms. Okay, so I can call this for A, for B. All right. Now there's also a similar thing for the quotient rule for logarithm, for first exponentials and then logarithms. The quotient rule. Okay, so if you understand this, then the quotient rule is a simple modification of all these things. If you'll allow me, I will just replace it by appropriate thing without having to erase too much here. So you get a quotient rule for exponentials, namely divide by, and then you get a difference here. So, and then the corresponding quotient rule for logarithms, you might be able to guess that you replace that by a dividing quotient, and this is a subtraction. So over here, these definitions of x and y still can be taken to be the same. And then this will be replaced by, you want to show that the logarithm base b of m divided by n is x minus y. But this is equivalent to m over n is equal to b to the x minus y. But this we know is b to the x divided by b to the y, and this is true because of the corresponding quotient rule for exponentials. Okay. Okay, so I just can change the words really, and just a few things like the product to a division and a plus to a minus sign in a few places, and the proof is the same, follows the same procedure. There's also a power rule. A power rule follows from the rule for the multiplication rule. So the 6 power rule. Or you can guess it from the product rule for logarithms. So the power rule for logarithms, when applied to the product m times itself, m squared, the product rule tells you it's log v m plus log v m. So m just becomes m in the product rule. Okay. And this means that we're just taking 2 times the logarithm base b of m. Similarly, if you took the product of 3 copies of m, 3m times itself, so m cubed, then it would be log base b of m squared, which we know is 2 log base b m, plus log base b of m again. So it just becomes 3 log base b of m. So each time you add a power here, you add an extra term log base b of m here. And so, in general, for n in positive integer, this gives you n times log base b of m. Now n can be made into any positive real number, positive or negative real number. If you have a negative integer here, then you would use, well, you can use the quotient rule. Quotient rule says, well, this is just 1 divided by log base b of 1 divided by m to the n. Right? And this is log base b of 1 minus log base b of m to the n. But that's just by the original product power rule. This is 0, because log base b of 1 is always 0. And this is minus n log base b of m. Okay, so that's the original. So that shows that, yes, if you have a negative exponent here, a negative integer here, then an integer will come out and be multiplied by the logarithm in front. Okay. And if you have a fraction in here, a rational number, then it again works. So n can be replaced. If you approximate any real number by a rational number, it again works. So this identity is actually true for all real n. So you could write it like this: log base b. Usually I like to reserve n for an integer, actually a whole number even, but so if I replace it by a, then I can say, well, no, it's a real number. Any positive or negative real number. Okay, so that's the power rule. Why does it work for fractions, you may ask? Let's see. Good question. Log base b of 1, let's say 1 over, or p over q. So you may ask that question. Why is that equal to p over q log base b of m? Okay, well first let's try the case. We've already done the case where q is 1. That's where p is a positive integer. P and q are both integers. P will be any integer, positive or negative, or 0. Q will be a natural number, so whole number greater than 0. 1, 2, or so on. And P and Q should be relatively prime, which we know is, it means they have no common factors. That's the GCD function. GCD of P and Q is 1. So anyway, but the fact is they're integers. Let's see if this works for, so we know it works for Q equals 1. So what happens if P is 1? And we'll look at this simple case. How do I know this is true? Okay, well, I just put the Q on this side. So multiply both sides by Q. And I replace M by, let's call N, M to the power Q. And this expression becomes, 1 to the Q, 1 over Q is equal to N. So this means M, when I raise everything to the power Q on this equation, I get M is equal to N to the power Q. So this will be replaced by N, and this will be replaced by, I'm just left with the log base B of M on this side, which is N to the Q. So this whole thing is equivalent to something we've already got before, the power law for Q an integer. So that's true. So we're just changing it into, the power then can be changed into a rational number by inverting here. And for a general case of P over Q, we could do a similar thing where we can combine this operation as 1 over Q to the power P. And then log base B of that will be simply the P comes out first. I'm left with M to the 1 over Q, and then the 1 over Q comes out second, and I get P over Q. And that proves it. So I combine my simpler results here to prove the general expression here, and use the rules for powers that are integers, which I knew from before, which I learned from before. All right. Okay, so let's do some try-it problems after a little bit of this theory, once we know what the rules are. Okay. Oh, and why can we always conclude it's also true for any real number? Okay. Well, it's because the rational numbers are dense in the real numbers, and we're pretty confident that the logarithm function is it's a nice function, so it's continuous. And so if we go closer and closer to a real number by approximating by rational numbers, A, then we can, and if we know that this is true for rational numbers always, then by continuity of both of these expressions, we can conclude that it's true for real numbers as well. So by the density of the rationals in reals and continuity of the logarithm function. And the exponential function that's also used here. Okay. That will imply this for the reals, for any real. All right. So now let's do some examples. So this theory is sort of fleshed out into more understandable terms. It's always understand something well if you can do the examples. So try number 1. Okay, so this is to do with expanding logarithms. So you're asked to expand log base b of 8k. All right, so the idea of expanding is similar to what you would do in polynomials. You would take all factors, and you would, if you have brackets, grouping factors, and those would be multiplied together, then you would use the distributive law to expand all those products into a sum of terms, and then simplify by adding like terms. Okay, so this idea is similar because you want to recognize that this expression is a product of two numbers, and you want to write the logarithm of the kind of the most simple product, the most simple factor that you can find. So in this case, if it's a numerical, if it's a number like a whole number, then you want to write it in its prime factorization before you expand it out as a sum of logarithms. Okay, so what this is then is log base b of 2 cubed times k. Okay, so those are the prime factor here is 2. I have to raise it to the power 3 to get 8. And this factor I don't know, so I just leave it as it is. And then I write out this as log base b of 2 cubed by using the product rule for logarithms. The logarithm of a product is the sum of the logarithms. Okay, and then I use the power rule here. So the 3 comes outside. The logarithm of a power is the power times the logarithm of the base. Okay, so that's the expanded version. I don't know how to write k in any simpler way like I've done here because I don't know what k is. K might not even be a rational number. It might be, or it might not be a positive integer. It might be a real number, but it should be positive at least in order for this to be defined. Okay, so when writing expressions with variables, what I've done here, it's important to recognize any restrictions because in the final result and to simply note them down. It's always helpful to note them down, like I've done here. Okay. Later we'll see when we solve logarithm equations, we might get solutions which, when we plug them back into the original equation, we get something that doesn't make sense. These restrictions are violated for such possible solutions. So those are called extraneous solutions, as we'll see. They're possible candidate solutions, but they get ruled out for some reason. And we can't include them in the solution set in the end. Okay. So the next example is, try it number 2, is to again expand this expression log base 3, and I think the full expression was given as 7x squared plus 21x divided by x times or 7x times x minus 1, x minus 2. So expand this. All right, so the idea is expanding. In expanding, you want to first factor the polynomial into the simplest, or the product of the simplest possible factors. So try to factor it completely, and then look for any cancellation. If there's a quotient here, we might have a cancellation between factors up in the numerator and in the denominator. And once we do that, then we can write everything out into a simple sum of logarithms of simple factors separately. Okay, so here let's factor the numerator. So we get 7x outside of x plus 3 comes outside, and then we have 7x, x minus 1, x minus 2. It's already in factored form. So we can cancel as long as x is greater than 0, or actually not equal to 0. That's one restriction. Then we can simply cancel these two factors. If x equals 0, then we don't have a well-defined expression. We have 0 divided by 0, which is undefined. And so we can write the remaining factors, or the quotient of the remaining factors, as a sum of logarithms. As using the quotient rule, it's log base 3 of x plus 3 minus the log base 3 of this product, x minus 1, x minus 2. Great, and I should write these now expressions. These expressions here depend on x plus 3 being positive, and this has to be positive as well. And if I split them up, I into x simple powers x minus 1 and x minus 2. By using the product rule. Okay, so the minus sign is in here, and the product rule says you add. You separate these and add them, the logarithms. But since the minus sign, the sum comes inside a bracket, there's a minus sign outside, therefore when you expand this, the minus sign changes this to a plus sign. Okay, so what we get at the end is log base 3 of x plus 3 minus log base 3 of x plus 1, x minus 1 minus log base 3 of x minus 2. These are all log base 3s. And in order to write it like this, I need these arguments to be both positive. All three arguments should be positive. So these will be true when x is at the same time greater than minus 3, greater than plus 1, and greater than plus 2. The only way that these are all true at the same time is if x must be greater than 2. Right, these must be true at the same time, so and. So it's the intersection of these three sets on the real line, which is simply the set of all reals greater than 2. Here's minus 3, here's plus 1, here's plus 2. So it's this set intersect this set, which is just the set of all real numbers greater than 2, right? Okay. Well, that's at least the book's method. I would observe that you could have solutions which are outside this domain, this interval, but you would then you could use the absolute value sign. Okay, you'd have to have this product being positive first. So you've canceled this as long as x is not equal to 0, so that cannot be a solution. And what you have is, you just need that this factor is greater than 0. So you could have all x in this solution, but you could also have x between -3 and 1. And this product here will then be positive. So this is a more general restriction on this set. If you're in this range, though, these factors must be, you have to use absolute value signs here and here. Actually, here you don't need them. Sorry, here you don't need them because x plus 3 is always positive for any values in this set. But here you do need it, and here you do need it, because the x minus 2 could change sign depending on whether you're above or below 2, and this could change sign depending whether you're above or below 1. Okay, so this would be the kind of correct, most general final result here. But if you just have brackets here and have this restriction, then I would accept that. All right. Number 3. Expand. Well, okay. Technically, I would have to be clear that yeah. You should try to be clear. When you try to solve an equation, for example, then you want to find all solutions. So that means that if you really want to know where the full domain of this function is, what values of x you can have, you must solve the rational inequality where you make this equal or positive. And when you restrict that to be positive, then you must, in order to find all solutions which are positive for this function, then you'd have to do as I did here, and then you would get these two sets together. So it'd be the union of this plus the union of this interval. Okay, so anyway, sometimes the domains could be a tricky thing. All right, so ln of x squared is equal to, expand this. And the answer is simply 2 ln x if x is positive. But you can also write this as ln of absolute value of x squared, because x squared is equal to the absolute value of x squared. And this is equal to 2 ln absolute value of x. And here you don't need a restriction on x, only that x is not equal to 0. But x could be negative, and what you're doing here is first taking the absolute value of that negative, and then you'll get a positive, and then you can take the logarithm, the natural logarithm of that, and multiply by 2. Okay, so this is the original function is well defined for any x not equal to 0, because the square is always a positive number. And so you should be able to write that the final value for any non-zero x. Okay, remember how the absolute value function is defined. So if you do want to, you can write it as a piecewise defined function. It's 2 ln x if x is greater than 0, and 2 ln minus x if x is less than 0. And it's not defined for x equals 0. Okay, so I'm just giving, the book gives you some simple solutions, assuming sort of a more restricted domain. And I'm kind of giving you a more general solution based based on the largest domain you can find for that function. Okay, I hope you see the difference. I hope it makes it clear here. Power law in reverse. So suppose you're given, this is number 4. This is section 6.5, by the way. As I said here, so try it number 4. So the power law in reverse it just means that we start with a simple expression that where the products or the logarithms may or may not be simple factors, but we want to put everything within the same logarithm. So we want to take the 2 and put it back in here. And so we can see by using the power law in reverse, if we take 4 to the power 2, then we get the same thing. And 4 to the power 2 is 16, so we get log base 3 of 16. Okay. So that's the answer for that one. Number 5, log of x squared y cubed over z to the 4th. And you're asked to expand. All right. We'll assume that x, y, and z are all positive. And of course, if the base is not shown, and we have log, then that means it's base 10. Base 10 is assumed. Okay, so this becomes, using the quotient rule, we would write this as a difference. Using the sum rule, we write the numerator as a sum of logarithms. And then using the power rules, we'll get coefficients coming out 2, 3, and 4. So writing it all in one step, we get 2 log base x, log base 10 of x, plus 3 log of y, minus 4 log of z. And these assumptions allow us to write these arguments in this way. Okay. If you allow for more values of x, x could be negative and z could be negative as long as they're still not 0, because we have even powers here. And then we would write this as we still need to require y to be positive, because otherwise this power would give you a negative number. So y still must be positive, but z could be anything non-zero, x could be anything non-zero, and then we'll get the 2 will come out, but it will be an absolute value sign here left. The y will stay the same, and minus 4 log base 10 of absolute value z. Okay, so that's more generally. That's a more general answer for more values of x and z and y. Well, I haven't really extended the values for y, but for the other variables, yes, I have. Okay. Try number 5 then. Sorry, 6. Sorry, we're done 6. I beg your pardon. This was number 5, and this was number 6. I missed number 4. Okay, so number 4 was the ln. Simplify this. Ln of 1 over x squared So again, I use the quotient rule for 1 over something. When applied to the reciprocal, gives us log base b of m with a minus sign. Okay, so if I take a number m and I take the reciprocal of that, then the logarithm of that reciprocal will simply be minus the logarithm of the original value. So this follows from the quotient rule. It's a special case of the quotient rule. Or I take the denominator, or the numerator to be 1. Okay. So from that quotient rule I just get minus log ln natural logarithm of x squared, which from my previous problem is minus 2 natural logarithm of the absolute value of x, where x is not equal to 0. So that was number 4. Number 7. Continuing our sequence here. Natural log of 3 cube root of x squared. What is the expanded form of this? The expanded form, again, involves writing the arguments of the logarithm as in as simple a way as possible. Here the argument of the logarithm is not very simple. Everything is under the same, everything is put together within the same logarithm, but we'd rather have the factor inside the logarithm to be simple and everything else outside the logarithm to be complicated. So can you see the difference? So in one case, you're putting all the complicated stuff inside the argument of the logarithm, and in the other case, you're making the stuff inside the logarithm, the arguments of the logarithm, to be as simple as possible, and all the complicated stuff comes outside. Okay, so here, again, for x positive, what do we get? The cube root corresponds to, so I'll write this all as 1 power, corresponds to a power 1 over 3. And in taking successive powers with the same base, or with one base, and then taking a power of that new base, that corresponds to the product of the powers, the product rule for powers that we know from exponentials. And so the product of 2 and 1/3 is 2/3. So I can rewrite this as x to the power 2/3, and then I can take, this is a rational number that I know I can use the power law for that, and I end up with 2/3 ln x. How about expressions like this? Ln of x squared plus y squared. Okay, so now this is very similar to square roots. Can I expand this? If I get square roots, can I write it as square root of x squared plus the square root of y squared? The answer is no. Okay, you can easily find numbers for which this doesn't work. X equals 1, for example, and y equals 1 gives you the square root of 2 on this side, but on this side you would get square root of 1 plus the square root of 1, which is 2, which is not equal to the square root of 2. Okay, so that's not true for just one single pair of numbers. Therefore, it's not true in general. Is it true at all for any x and y? Well, yes, it is true if you take x to be 0 and then y could be anything, and then it will be true, but only for those values. But in general, because it fails for one value, you cannot say this holds in general. So never ever, safe to never ever use that rule, unless you're absolutely sure that in the special cases you have, it's true. Like 1 of x or y is 0. Now in the same way that you cannot use, there's no such law here. It's true for products, by the way. If you have a product here instead of a minus sign, then you can do it. Okay, but don't confuse that rule and say that it automatically holds when you change the multiplication to a plus sign. Here, this does not expand. If it's a multiplication sign, then you could use the product rule for logarithms and write this as a sum of two logarithms. But here, because you have a plus sign, it doesn't work. You can't say that the logarithm of x squared plus y squared in brackets is equal to the log x squared plus. So neither of these is true. So this is not equal to log base whatever 10 of x squared plus the log base 10 of y squared, nor is it equal to the product. Okay, it's just not equal. So you could easily find examples. So for example, 1 and 1 again gives you log base 10 of 2. Oh, this is running out. I'm using the wrong one. Okay, so log base 10 of 2 on one side, and on this side you would get zeros. But log base 2 is not 0. Log base 10 of 2 is not 0. Okay. Or the product rule also doesn't work for that because of that example. All right. So when evaluating expressions like this means this expression is in brackets. So if you for the square root, it's in brackets. You think of this as being a bracket. Okay, that's why I put this hook in the end. It's to show that this line covers over everything that's underneath it. And you could stop right there. Okay, so this logarithm is of a single factor. You have to first evaluate the brackets first. So the x squared plus y squared, and then you take the logarithm of that. So that's what this operation means. You can never assume that you can interchange the orders of operations easily. Okay. Okay, that could easily lead to mistakes, to wrong calculations, to losing marks unnecessarily. It's always safe to keep it in the form in which you found it, unless you're absolutely sure you can use a rule. All right. In other words, it's better to get a number correct and unsimplified rather than assume some simplification and actually get it wrong. Okay, you lose more marks if you get the answer wrong. Whereas if you have the correct answer, but it's not in the final simplified form, at least the answer is correct if you use the right rules to simplify. Okay. Or use a calculator, it can be shown to be correct. Now the next example, number 8. I would use a different color for a while, blue. So number 8. Okay, so this expression here, square root, you want to simplify this or write it out in expanded form. So 2x plus 1 squared times x minus 1, all under a square root, and then divided by x squared minus 9. Okay, so assuming all these factors are positive, which is true when x is greater than 1, 2x plus 1 is greater than 0, and x minus 3 is greater than 0, and x plus 3 is greater than 0. So I've thought of this as already in factored form. So I want to factor all expressions so I get the simplest possible factors. And then I'll assume that all those factors are positive, and then expand it into this form. So the square root becomes a power 1/2. So I have to raise these two to the power 1/2. So I would get 1/2 ln x minus 1. And now the 1/2 multiplies by the 2 and gives me 1. In other words, if I take the square root of just this part, I just get the simple factor 2x plus 1 without any power. So that will become ln of 2x plus 1 minus ln of x minus 3 minus ln of x plus 3. Okay, both of these are negative because both of these factors sit in the denominator. Okay, this is a 1/2 because of the square root, which applies to this factor. But here the two powers I'm taking of 2x plus 1 are 2 and 1/2, and you multiply them together and it gives you 1, and that's why I have a coefficient of 1. In other words, it's by itself here, ln of 2x plus 1. So the coefficient of 1 in front of the logarithm. Okay, so continuing on, number 9. Okay, going in the opposite direction is called condensing. So condensing is the opposite of expanding. Okay, so here's the expression I want to condense. Log, get base 10 of 3 minus log of 4 plus log of 5 minus log of 6. It's a try-it problem. Try it number 9. Okay, so I put everything together within the same logarithm, and I do that using the quotient rule and the product rule for logarithms. So any sum here becomes a product in the numerator, and the difference here, the negative signs correspond to putting those factors in the denominator. Okay, so if I expand this out, I can see I'll get the logarithm of the numerator minus logarithm of the denominator. And when I expand both numerator and denominators using the product rules, I get sums. And here the sum will give a minus sign for each term in it. Okay, so writing it out explicitly. This has two minus signs because I have a bracket. Where when I expand this will be inside the bracket, and the minus sign will be applied to both terms within that bracket. So then I get this. Okay, so that's my answer. All the numbers are positive, so I don't have to worry about restricting values of x to certain domains. They're all, you can see that they're positive. If I get if I have log base 2 of minus 2, what happens here? So that's not defined. So don't be, you don't have to go any further with that. Once you see this, this must always be a positive argument in the logarithm. Then number 10, try it number 10. Log base, again we're talking about log base 10 here when we don't have an explicit base shown. Log of 5 plus 0.5 log of x minus log 7x minus 1 plus 3 log x minus 1. And here we need to do some condensing. So condensing is just the opposite of expanding. So we write all of these first as logarithms of something inside each of them, and then we'll use so this will need the power law in order to take the power inside and write it as x to the power 1/2. This will also require, we have to take the 3 in and call that x minus 1 cubed. And then we'll use the power law and the quotient law to bring everything under one logarithm. So we can actually do this all in one step. And write it as log base 10 of 5 times x to the 1/2 times x minus 1 cubed divided by 7x minus 1. So all the positive powers get placed in the numerator. Positive coefficients are either plus 1 or minus 1. All the plus 1 coefficients get their factors put in the numerator, and the negative factor gets, the factor with a negative 1 in front of the logarithm gets placed in the denominator. And we should possibly put restrictions on this so this makes sense, so we're not getting into negative values of the argument of the logarithms by saying, okay, x is greater than 0 for this factor, 7x minus 1 is greater than 0 for this factor, and x minus 1 is greater than 0 for this factor. Which is true when x is greater than the largest of these. This is x greater than 0, x greater than 1/7, x greater than 1. Well, if x is greater than 1, then it's also greater than 0 or 1/7, because 1 is greater than both 0 and 1/7. Okay, so that's the only restriction we need for this all to make sense. Now, let's look at an application from chemistry here. Namely the pH. Okay, so pH, the pH is a number used in chemistry to describe the acidity of a substance. So an acid is basically a chemical like this. So hydrochloric acid would be HCl. Okay, so H2SO4 is sulfuric acid. I'm just recalling things from my chemistry in grade 12 here. So what happens if you dissolve this in water is that the hydrogen ions, which are positive, +1, dissociate from the chlorine atoms, that the water molecules surround them and they separate. And the H pluses, they become, it's a very active ion. The H pluses increase the concentration of H plus in the water. Okay, actually originally water, pure water by itself, has this reaction naturally. So it will dissociate into H plus ions and OH minus ions. These are hydroxide, this is hydrogen. And pH level of pure water, the concentration of the H pluses in pure water will be 1 times 10 to the minus 7, measured in molar, which is moles per liter. Okay, so a bit of chemistry. Moles, a mole is 6.023 times 10 to the 23rd. It's actually a number. The number of atoms of, or the number of particles H plus in 1 mole, 1 gram of H is going to be equal to this 1 mole. So 1 mole is 6.023 times 10 to the 3rd particles or constituents that is under consideration here. Okay, in this case it would be hydrogen ions. Okay, so in just pure water, you get this concentration, but if you mix in an acid in water, then this concentration will go up. And the pH is a way of measuring the relative concentrations. And the way the pH is measured is by taking the base 10 logarithm. So you take actually minus the base 10 logarithm of the concentration of hydrogen atoms. Okay, so in this case for pure water, the pH level is the natural log, and you have to use these units of molar to get this right. If you use the wrong units, you'll get different numbers. So log base 10 of 1 times 10 to the minus 7. The log is the base 10, so you take, this is just 10 to the power minus 7. So the minus 7 comes up front, and you get 7. Usually write it to a single decimal place. The minus sign will cancel the minus sign here. Okay, so if you increase the concentration of H plus, then you typically can get, if it's very, very concentrated, then you can get concentrations like this, like about 1 molar, let's say. What would that correspond to? Well, if you take the log base 10 of that, pH level there would be 0. Okay, so 0 is lower than 7. So lower pH corresponds to higher concentrations of H plus. Now if you mix a base in with a substance, a base is something like, let's say, KOH. So that's potassium hydroxide. KOH dissociates, you get a plus potassium ion and OH minus negative ion. And the negative OH ions will tend to increase the concentration of OH minus. And any excess hydrogen atoms will be canceled. You'll get more water. And when this cancellation is done, you'll get a lower concentration of H plus than you started with. So you can actually reduce it to smaller than 1 times 10 to the minus 7. So the lowest concentration might be H plus 1 times 10 to the minus 14 molar, in which case the pH would simply be 14. So the higher pHs correspond to more basic substances. So that's sort of acids and bases in a nutshell. Please take a chemistry class to learn more about this, but the basic idea is that you'd use logarithms. And so this is an example of calculating logarithms. You'll need to know how to calculate using logarithms if you wanted to take chemistry and learn about bases and acids. So the example in the number 12 or number 11 tells you how, okay, number 11 is, no, number 12. How does pH change when the concentration of positive hydrogen ions is decreased by a factor of 1/2? Concentration of positive hydrogen ions is decreased by basically multiplied by 1/2. Now, the previous example to this in the textbook, which is worked out for you, asks a similar question. It says, how does the pH change when the concentration of H plus is multiplied by 2? This is multiplied by 1/2, so it's kind of the inverse operation of the previous problem. And in the previous problem, you realize that the pH will decrease by 0.301. So in this case, the pH should increase by 0.301. Where does this number 0.301 come from? It's an approximation to the natural logarithm, or the log base 10 of 2. Okay. So let's see how that works in this case. So I just changed the sign from the example. The example says it decreases by this result. So I'm just going to guess when you do the opposite, divide instead of multiply by 2, then you simply add that to the pH. And that makes sense because increasing the pH decreases the concentration of hydrogen ions, as I just was explaining here. Okay, it's because of the negative sign here in the definition of the pH. H plus increases, the logarithm will also increase, but because of the minus sign overall in front, the pH will decrease. Okay, so let's see how that works. So if I take my original hydrogen concentration, the pH of that is minus the logarithm of this concentration. So call it 0, indicate the starting concentration. Now I double this, or sorry, I divide by 2. Now to get the new concentration, I call it pH1. Again, I take the minus the logarithm of this whole thing. Okay, now what is this? Well, I have a minus sign, and in brackets outside, I get the logarithm, and I use the quotient rule for logarithms. So I get the log base 10 of this hydrogen concentration as before. That's my one factor. And then I subtract the log base 10 of 2. Okay, so that's a quotient rule for logarithms. And now I just expand this using distributive log. So I get minus the log base 10 of H plus the log base 10 of 2. And this minus sign has become a plus sign because of the minus in front of the entire brackets. I take away the brackets and I get this. And so this is the original pH, which I call pH 0. So it's the original pH 0, whatever it was. We're not told, but we don't really need it. plus this log base 2, which is evaluated as 0.301. Okay, so when I decrease the concentration of hydrogen by plus, then that increases the pH by 0.301, just as I said. So that indeed is my answer. Okay, so the new pH, pH 1 is equal to the old pH, pH 0 plus 0.301. Okay, so hopefully that will help you understand chemistry together, should you choose to take chemistry. All right, so now change in base formula. So these are some interesting and useful properties now which help you calculate more general logarithms using a calculator, for example. So as I mentioned before, calculators usually only have as their functions the simple buttons log base 10, or without any exponent shown. It's always log base 10, or the natural logarithm. Suppose you want to calculate a number log to the base b of another number m. What should you do? It's not on the calculator. Usually it's not. Well, you use a change of base formula. What is the change of base formula? Well, I can introduce a third number, arbitrary, as long as, well, b has to be positive and not equal to 1. So I can introduce another base and express this whole thing as the log base n of m divided by the log base n of b. As long as n satisfies the same properties for a base. N is not equal to 1 and greater than 0. Okay, now why is this true? Well, let us do a little bit of algebra. Let's call this whole thing x. So I want to evaluate x in a different way than this. Okay, so let this whole side, the left-hand side of the equation, be designated x. Okay, so now I can rewrite this in its exponential form, namely b raised to the power x is equal to m. Okay, so that's the exponential form. Okay, now I want to solve for x. I don't want to just go back the same way I came. I could do it that way, but then I get the original expression, and I haven't progressed any further. But I want to solve for x rather in a different way than just going back. Okay, so I mean, if you go back, you're just going in a kind of a circle here. So let's try something different. Namely, I'll take the logarithm base n of both sides. All right. So because the logarithm function is a one-to-one function, because it is a function, therefore, if I plug in the same argument, I should get the same answer. So this should be log base n of b to the x should be equal to log base n of m. Okay, so now I have this expression log base n of b to the x. Well, I can use now the power law for logarithms and take the x outside. So I get x times this whole logarithm is equal to log base n of m. And now we can solve for x just by dividing both sides by log base n of b. As long as b is not equal to 1, which is assumed here. Right? Otherwise, this would be simply 0 for any base n. And so then I would get log base n of m over x is equal to log of base n of m divided by log base n of b. And that's what I was asked to prove. That's what I was going to prove. So that proves this formula. So it's called the change of base formula. Okay, so now, by the way, this shows that if you do a change of base, so given a function log base b of x, then you can write it in terms of any other base. I'm just replacing x by, or I'm replacing m by the variable x. Okay, so by replacing the base of a logarithm function, a simple logarithm function, by another base, it corresponds to multiplying, you can get this new function with the new base if you just multiply this old function by this factor here. So I'm just putting this factor over on the other side. So this is log base b of x times this overall factor log base n of x. And this is like a constant factor that comes out in front. It doesn't depend on x. Okay, so it's a change of base constant. So it shows that what I was showing before, the logarithm function with different bases, the logarithm functions with different bases correspond to, they're just vertical scalings of each other. They correspond to multiplying by some overall factor in front. Okay, so all right, so that was something I was pointing out earlier in previous lectures. It comes from this change of base formula. What's another thing I can conclude from a change of base formula? How about this expression? I take the log base b of any m, and it's equal to the reciprocal of the log base m of b. So here I need m to be, again, positive and not equal to 1. So the argument itself could become a base. I could just switch the base in the argument, and it corresponds to taking the reciprocal. Okay, so why is that true? Well, here you would use the base, change of base formula, where I change the base. I can choose the base to be anything I like, as long n could be anything I like. So here I'm choosing n to be m in the change of base formula. And then I get log base m of m itself. The argument stays in the numerator there. And log base m of b. But the log base m of m is always 1. And hence I get this expression. So that verifies the expression with these properties. B is also greater than 1 and not equal to, or not equal to 1 and greater than 0. All right. So let's use that in some examples here, both of these formulas. Okay, here's a try-it problem. Try-it number 3 of this I started a new section here. This is section 6.6. I'm sorry, maybe I'm wrong. Maybe this, we're still in 6.5. Let's see. Yeah, we're still in 6.5. This is number 13, sorry, I think. So now we have this expression. Log base 0.5 of 8. Change to a quotient of natural logs. Okay, so what do they want us to do? What is this question asking us to do? Well, change to a quotient of natural logs, that suggests using the change of base formula, where you've introduced the new base e to get natural logarithms. So the log base 0.5 of 8 is equal to the natural logarithm of 8 divided by the natural logarithm of 0.5. That's what we would get using the change of base formula. Okay, and then we can calculate this using our calculator if we wish, if we have the natural log function on it. But in this case, I think we can go further. Let's see how we can go further without using a calculator. The way I'll go further is by expressing both these numbers as powers of 2. It turns out that they can be easily expressed as powers of the same base, namely 2 cubed goes up here. Down here it's log of 1 over 2, which is 2 to the power minus 1. The powers come out front using the power rule for logarithms. So we get minus log base, natural log of 2. I would read it minus ln 2, 3 times ln 2 minus ln 2. Okay, so now we have the same factors here and here. They're both non-zero, so we can cancel them. And 3 over minus 1 gives us minus 3. Okay, so even though the expression here can be calculated using a calculator, and I would get some irrational number up here, and I would get an irrational number up here, somehow in the end, the irrational part would simply cancel, and I would get a rational number in the end, minus 3. Okay, something seems to have gone funny here. It says my stream health is good, but I can't see. Possible example. Okay, well sometimes you don't get all that simplification down to a rational number, and you still have to use a calculator in the end. But it's nice to try to simplify it as much as possible so that you're ready to do the steps requiring a calculator with the least possible effort. So let's see what I get for this, in this case here, for this example. Log base 5 of 100. All right, so log base 5 of 100 is, let's say, log base 10. So we'll use base 10 as our base. So this is log 100 divided by log of 5. The log base 10 of 100, it's 10 squared, so this is over log base 10 of 5. Okay, and then we sometimes 0.301. I could probably use that to get an answer here almost by hand. So how do I get log base 5 if I know that? Well, log base 5 times log base 2, plus log base 2 is equal to what? Well, using the sum rule for logarithms, or the product rule for logarithms, this is equal to log base 5 times 2, which is log base 10. But the base is the same as the number, so that's just 1. Therefore, log base 10 of 5 is 1 minus log base 2. log 2, sorry. So 1 minus 0.301 is 0.79, all right, 699. Which is about 0.7. And then I divide that, so 2 divided by 0.7. So that's about 20 over 7, which is 7 into 20 goes twice, remainder 6. 7 goes into 60 8 times. Okay, so we get this decimal repeating 28571. Okay, so I get it. That's approximate because this I made an approximation here. So this should probably be only get into three significant figures. Same as the number of significant figures here. Not decimals, but we count the non-zero, starting from the first non-zero digit to the last non-zero digit. Include all those, and those are the number of significant figures. You might get 0 digits in the middle, but you have to count those. Or the last one might be 0, but in that case you would actually show the zeros. All right. Okay, so this is what this is the answer that I'm getting here. Close to it. Log base c of 100. Okay, well that's log base c is the natural logarithm, so this would become ln of 100. So I could do this using a calculator that way, or you could write this as 2 ln of 10 in a more simplified way. Okay, or I could use this change of base. I could either change the e in the 100, and I get 1 over the natural, sorry, 1 over log base 100 of e. Or I could write it as log 10, 100 over log of e. Log 10 of 100 is 2. So it's 2 over log e. Okay, so it's interesting how there are different ways of writing the same numbers. If you check these answers, they should be the same if you use a calculator. And you can see right away that this should be true because of the interchange of argument with base formula. All right. And so, okay. Now the last section I want to touch on here has to do with equations involving exponentials and logarithms, and solving such equations. Okay, so this is section 6.6, logarithm equations, or exponential and logarithm equations. Let's see how this works. So some simple examples will help here. And using the one-to-one property is very important here. Okay, so if I can reduce the equation to something of this form, 5 to the power x, or b to the power of x is equal to b to the power y, where b is an acceptable base, greater than 0 and not equal to 1, then I can conclude from this at x equals y. That's my one-to-one property. And so it'll allow me to solve a wide variety of these equations. So let's try it with number 1 here. Try it number 1. Here I have 5 to the 2x is equal to 5 to the 3x plus 2. Okay, so using the one-to-one property, I have a base equal b equals 5. I can conclude then that the exponents are the same on each side. So 2x is equal to 3x plus 2. Now I solve for x in the usual way. I get minus 2x on both sides. Cancels the 2x here and gives me x here. I put the 2 on the other side, I get a minus 2. So my answer would be x equals minus 2. Then I should check by plugging that in. And on this side I would get 5 to the power minus 4. And here I would get 2 times 3 is 6. With the minus sign, minus 6 plus 2 is again 5. Gives me 5 to the minus 4. Minus 6 plus 2 is minus 4. So I get the same thing. And that checks my solution set. So the solution set is then minus t. Let's try it number 2. 5 to the 2x is equal to 25 to the power of 3x plus 2. Okay, so now here I have different bases in my starting equation. So again, I'm asked to solve for x. And check. I throw that in because I always want my students to check their answers. It saves them a lot of grief. I always like it when students get the answers right. And checking will certainly help you do that. If you find you check it and you don't get, the right-hand side does not equal the left-hand side, then you must have made a mistake somewhere. And it helps you to localize to find out where you made your mistake. Okay, so here, how I would solve this problem is put both numbers under the same base. And then we'll use the one-to-one property. Okay, so we can do it in one of two ways. We could write 25 as 5 squared, and then when you raise that to the power 3x plus 2, it's the same as multiplying the 2 by the 3x plus 2, so that becomes 5 and then 6x plus 4. So we could do it that way. Then we get 2x is equal to 6x plus 4. And then solve for x here, and I get minus 4 is equal to 4x, x is equal to minus 1. Okay, so there I did it using the base 5, but I could also do it using the product rule for exponents up with this one to make this 25 raised to the power x. Okay, so either way you do this should give you the same answer and could provide a check for you, but then you equate x equal to 3x plus 2, solve for x, and you get, again, x equals minus 1. So it checks this original solution. And you can also plug it in directly and check it to verify it. You get 5 to the minus 2 for the left-hand side, and for the right-hand side you get 25 to the power, and raise this to the power of minus 3 plus 2 is minus 1. And 5 squared is 25, so no matter how you do it, minus 1 does look like the correct answer, so that's my solution set. So the key here, the trick here, is to express both sides, all terms or products here, with respect to the same base. And once you get an expression raised, some base raised to some power on one side and the same base raised to another power on the other side, or at least a different expression, then you know that those two expressions in the power exponent of that base must be equal. And then you can solve from then on. Okay, let's try number 3. Section 6.6. 5 to the x is equal to square root of 5. Again, I express this as the same base. You can do it as 5 to the 1/2. And then immediately I get x to the 1/2. So that's the answer. Or write the solution set as the set consisting of just 1/2. Number 4, 2 to the x is equal to minus 100. So it's a bit of a trick question here. But it's not hard to see that, well, you cannot solve this because you would need to take the logarithm of a negative number, base 2. Or you can see that 2 raised to any real number will always give you something positive, so it can never be negative. So here there's no solution. Number 5. Try number 5. Now you might have different bases here that cannot be expressed easily in terms of each other. So 5 to the power x plus 2 is equal to 4 to the power x. Okay, so I think that was an example. The try it example was different. It was 2 to the x is equal to 3 plus 1. So this is done in the book. I'll let you look at that. This is very similar. So you can use, the way I could do this is just use the trick of taking the log of base, whatever is convenient, say the natural logarithm of both sides. So we'll take the natural logarithm of this side, and it will, if this equation is true to begin with, then this will also be true. And then the power comes outside, so x times ln of the base 2, and this is x plus 1, the whole factor comes out front, ln base 3. Okay, so these are both, this is x times ln 2, this is x plus 1 times ln 3. So this then is actually a linear equation, which I can, in x, so I can solve for x by the usual techniques of solving linear equations. All right, so how I do that is I put all the terms with x on one side, and I combine like terms. Here the terms are x to the power 1. I only have linear terms, and the constant term, which is 1 times ln 3. So I expand this, and I get x times ln 3, and that term goes on the left side, equals, and I keep the remaining term on the right side, so ln 3 right here. Now ln 3 is bigger than ln 2, and so what I'll get is an overall, I can change everything by an overall I don't want to change anything, but I can express this as with an overall minus sign in front times this difference which will be positive. I know that because the logarithm function is always an increasing function. And so when I solve for x, positive, not equal to 0. So now I can divide this because it's not 0, and I get minus overall minus sign, natural logarithm of 3 divided by the natural logarithm of 3 minus the natural logarithm of 2. And remember, I can't do any cancellation here. I can't cancel these two because this is in brackets here. And it's a sum, or a difference here, not a product. So I cannot cancel it on 3 here. And so this will be the final answer, which I can then use a calculator to find a number for if I need it. Okay, so that was try it number 5. Try it number 6. Okay, so this has to do with equations of this exponential form. Y is equal to a e to the power k times t. All right. So this is often seen in physics, where you have t is a time variable, and k is some constant which indicates somehow either the growth rate or decay rate. If k is positive, then this is a growth rate. If k is negative, this is a decay rate. K is some real number. If it's 0, then there's no growth, and this will give you 0 always in the exponent, which will be a constant. So y is a constant function in that case. Here, a is some constant factor in front. So it's like the initial value. If you plug in time t equals 0, then this will be just 1, and y will be a. So a is the initial value of some quantity which might grow or decay in time, and k is a growth or decay rate. And t is time. Y of t, y is really a function of t, if y is a function of t, is the amount of a quantity of some growing or decaying quantity in time. Quantity at time t. So y of t is the amount of some quantity at time t. Okay, so this is an exponential growth or decay rate. So suppose you're not given the time first, but you're given the quantity, initial value, and then the quantity. So the initial value might be 20 in this case, and the final value is 100. So the question might be, how much time does it take to grow using this decay rate, which is given as 2? How much time does it take to grow from 20 to 100? And the answer is, well, you can solve this and write it as a logarithm and then use a calculator to calculate it. Okay, so if I solve using just solve it using my rules, I divide this side by this side and I get 100 over 20 e to the 2t. So solving for t is very similar to solving linear equations at first. At least I want to isolate this factor. Okay. This factor I don't touch. I treat this like my x. If I think of this as x, then this is just a linear equation. It really is a linear equation. And I can solve for x. X is equal to 100 over 20, which is 5. Okay, now I go back and I replace x by what I was calling x to begin with. And can I simplify this? Well, if I take the natural log of both sides, I want to solve for t specifically. So yes, I can keep going, but I take the natural log of both sides, and the natural log of e to the 2t using the inverse formula is just 2t. by definition of the logarithm, the natural logarithm. So this is then t is equal to, solve by divided by 2, natural log of 5 over t. Okay, so that's a number, and I can use a calculator to calculate that. All right. So the answer is probably a decimal like 0.7 or something, I'm guessing. Okay, you can check using a calculator if you need to find the final answer. All right, so that's an example of finding the time it takes for something to grow to a certain amount, given an initial amount, and given that it follows this decay rate formula. Okay, so try number 6. 3e to the 0.5t is equal to 11. Okay, so again, I divide by 3 on both sides. I solved in terms of e to the 0.5t by linear equation techniques. And then I take the natural log of both sides, and that gives me the argument here, it's 0.5t, and then the natural log of the rest on the other side, which is 11 over 3. And this is just to multiply both sides by, or divide both sides by 0.5, and that's the same as multiplying by 2. So I get 2 ln 11 over 3. And that's my answer. One can check, one can plug it back in and check using all the rules for logarithms and exponentials and verify that this is indeed the right answer. Okay, if I have an equation like this, note that this has no solution, because e to the t always gives you a positive number, and this will make this negative, whereas this side is positive. Number 7, if I have a more complicated expression like 3 plus e to the 2t is equal to 7, e to the 2t. At first, I combine like terms. These are both similar terms. I subtract this from this side, and this will combine using the distributive law as 6 e to the 2t. Then you divide both sides by 6, and I get e to the 2t is equal to 1/2. In the end, I'll get 2t is natural logarithm of 1/2, which is minus the natural logarithm of 2. And so t is equal to minus ln 2 over 2. Now how about something a little bit more complex? A little bit, not as a complex number, but a little bit more difficult. And that would be, let's try this equation. I just made it up, but it's kind of instructive. Let's find all solutions, solve this. So find all solutions in t that make this equation true. Okay, so now you see you have a bit of a problem here, because you have effectively different bases with the same exponent. So you can't just combine these two terms like I did over here. This is exactly the same base and the same exponent, so there I can do it. But here you either think of the bases as being the same, but the exponents are different. So here I cannot combine, right? These do not combine and give me anything. So this does not equal to either the product or the sum of the exponents. Right? You just have to leave it separate. Okay. But I can use the fact that this exponent is twice this one with the same base. And what can I do here? Well, I can let x equal e to the t. So we just notice this, that if you write x as e to the t, then this becomes 3 times x, and this becomes 2 plus, and this here will become x squared, right? Raise this to the power 2. When I square x, this gets raised to the power 2, and that's multiplying it's the same as e to the 2 times t. Okay, so now this is a quadratic equation. So I can solve for it in the usual way. Put all the terms on one side, equate it to 0, and then factor. So here I get x minus 1 times x minus 2. So there are two possible solutions, x equals 1 or x equals 2. Now to get the solutions in t, I have to write this out as in terms of t by back substituting this formula in here. So e to the t equals 1 is my first solution, and e to the t equals 2 is my second. Here when I solve for t, I see t can only be 0. And here, I take the natural log of both sides and I get t is equal to natural logarithm of 2, ln 2. Okay, so that's what I get for possible solutions. I should check this. Okay, and I see I'm going quite long in time here, so I better. Apologies, that one should check this, and what you get is for the t equals 0 case, you just plug it into the original formula. You get 1 here and 1 here, so you get 1 plus 2 is equal to 3. And so that's correct. So you should check both answers, because oftentimes you have what are called extraneous solutions, one of which works and the other one doesn't. In some cases, the worst possible case would be none of them work. So it's not good to suggest that something is a solution when it's obviously not, just by plugging it back in. So we should do that for both cases. T is ln 2. What do we get? That's a bit more complicated, but again, you can use the rules for logarithms to rewrite this. So remember that e to the ln 2, by definition, is 2, just using the inverse property for exponentials and logarithms. The bases are the same for both the exponential and the logarithm functions here. So you just get the argument that you put in here at the end. So if this whole thing is 2, then this whole thing, e to the 2 ln 2, is 2 squared. And this is 2. And this is 3 times 2, which is 6. So this side you get 4 plus 2 equals 6, and that's correct. All right. So I think I've gone long enough. I've introduced a few of these, all the laws that you would need to know, and done some examples. And furthermore, we looked at some applications like pH and exponential growth and decay here, practical examples which you might find useful in other courses. There's a few more examples that are done that I've yet to do in this section, namely involving extraneous solutions and solving other kinds of similar linear equations. And so I'll leave it at that, because after this I would like to quickly start trigonometry. So if you just go up to the end of this section, 6.6, I won't continue further than that. Well, the last two sections involve looking at exponential and logarithmic models, and it involves using a calculator usually. And the last section involves graphing the exponential and logarithm equations and solving equations by graphing. And again, I won't do that much because many of you don't have calculators, but we'll try to deal with similar problems as to what I've done here by Maple-T and so on. So with that, I'll sign off and bid you adieu and all the best for the next few days. I'll attempt to do the next lecture on Saturday, and so try to follow the schedule as usual, and then Monday. And I still have not given you assignment. Please, probably won't have the quiz on Monday because the assignment has not been, I want to give you a mastery assignment first before giving you the quiz. Okay, so take care and have a good day, Hudofis. Bye.